Hello everyone, here we'll be discussing chapter 8.1, which is a discussion on arc length. Now arc length, unlike area under the curve, is looking at a function, a curve of a function, from x values a to b, but again, instead of the area under the curve, we're looking at the length of the segment of the curve between those two x values. Now exactly how we're going to find that, and usually we'll call it capital L by the way, is we're first going to approximate it using some techniques we saw with estimating the curve, area under the curve with slices. So let's kind of create these slices. Now here I made it look like there are 5 slices, but imagine there are n slices, and we'll kind of use the usual labeling here. So x0, that'll be xn. The next one is of course x1, and the next 2, and so on. And the length between them, the difference between any consecutive x values, is delta x, which we know to be just the length of the interval, b minus a, over the amount of slices or rectangles, which is n. And now the magic kind of part is our approximation will be with straight lines. So notice this is a pretty good estimation of the area or the length of the curve. And the more slices you have, the more close it'll be to the actual length of the curve, from a to b, of course. Now, how we're going to find each of these is essentially by Pythagorean theorem. Now, I'm not going to go through a very rigorous proof of this, but I'll just kind of explain that, let's say you have some 2 points here. And let's say the x value here is xi, and this is xi plus 1. I usually do I and I minus 1, but it doesn't matter. Now, of course, their distance is delta x, and that's fine. In fact, if you take a look at this triangle and kind of zoom in, it will look something like this. Now, if you want to find the actual y values, you can project to the function. So this guy right here, for instance, will be, f of x I plus 1. And the other one here will be f of x of I. And I know that the image is getting a little cluttered, but again, just project the x values to the function, you get the y values. But instead of doing that, I'm just going to do this. I'm going to say this length is delta x. This length here is delta y. Okay? So notice that what we're dealing with is basically the this length here, which is going to be, well, the square root of delta y squared plus delta x squared. Now what you're probably expecting me to do, there's a square here by the way, what you're probably expecting me to do is somehow get delta y over delta x involved because that's the slope. In fact, we can definitely do that. Notice that if we divide the inside by delta y squared, we end up getting 1 plus, I guess it'd be delta x squared, we get 1 plus, I'm sorry, let me think. So if we divide by delta x squared, yeah, there we go. We get delta y squared over delta x squared plus 1 because it's delta x squared over delta x squared. But in order to do that, we kind of have to do some tricks. So I'm going to look at this length here. So basically what we're doing is to find the length here, we're saying the length is equal to the limit as n goes to infinity of the sum from I equals, I guess, 0 to n of these distances. And in fact, really it's to n minus 1. Because you kind of see, you're going from x0 to x1, that's one of them, and then going from xn minus 1 to xn, that's the other one. But it doesn't actually really matter how we index it. You'll kind of see the big part of this this explanation here is the inside of the sum part. So the inside of the sum will just be the lengths of these line segments, which are the hypotenuse of these right triangles. So I struggled a little bit to explain what's going on here, how we can get derivative involved. In fact, I haven't said derivative, but you kind of think it because it's the slope of this triangle image here, which is delta y over delta x. So to get delta y over delta x, this delta y we're expecting delta x to be on the bottom. So what I'm going to do is I'm going to just kind of see this for a second. We have this, and I want to divide by delta x squared. Why? So that when you split this up, you get delta y over delta x, quantity squared, plus 1, because if you split it up, you get, again, delta y squared over delta y squared, delta x squared, which is the slope all squared, plus delta x squared over delta x squared is just 1. And notice, since we're dividing by delta x, we better multiply by delta x squared. so that we have cancellation and we end up with just the original thing we're summing over anyways. Great. And since we're taking the square root of this, that's the square root of this, times the square root of delta x squared. So notice this part here in parentheses is the part in this radical, and if we split it up here, notice that the square and radical cancel. So this really just becomes the limit as n goes to infinity of this guy. And I'm going to rearrange these just because that's the way it's more traditionally written. Delta y over delta x squared and then delta x. Now there are a few technicalities of what I'm about to say, but just kind of let me say the following. Recall that the limit as delta x goes to 0 of delta y over delta x is just the derivative dy over dx. Namely, it's f prime of x. So in the limit, as n goes to infinity, notice as n goes to infinity, delta x will go to 0 because the denominator is going towards infinity. So in fact, this will indeed be the case. And we'll get f prime of x, quantity squared, a plus 1 in front of it, or a 1 plus in front of it, all under the radical. And what you'll notice here is if you treat the radical part as kind of like a function, let's call it like, if you want to call it capital F of x, which is probably not the best notation, but you can definitely do that. And by the way, this is technically of x sub I. Notice, this should look familiar because we have a limit of a sum of x sub I times delta x, and the limit that goes to the integral of that function without the x sub I, dx. So this is the integral of this expression dx. And of course, it's a definite integral from a to b. Perfect. So that's what we're going to finish this conversation as far as the explanation of the formula goes. But yeah, it's pretty easy to see where this comes from just based on the approximation of the length of the curve by line segments. And in fact, speaking of which, let me call it capital L for the arc length of the curve. Now, there are some kind of conditions, and the main condition, of course, is that we can only really do this when f is continuous on this interval. So I guess as a subscript here, or as a kind of keynote, let me say if, or I guess let me just say this, f of x must be at least continuous on the interval a to b, the closed interval a to b. Okay, and with that being said, I think we're good to go. And now we're going to take a look at some examples involving this. I only want to do, well, at least 3. So let's take a look and see how many we can get done now. All right, so here we have basically the formula we just developed in prime notation and in Leibniz notation, which I've kind of developed both actually as we went along. Or notice x is in between a and b, inclusive. Now, if we instead have a function in terms of y, so in this case x equals g of y, then we can say that the arc length of that curve would be the integral from c to d now of the same expression, only with g prime of x, g prime of y instead of f prime of x. And notice that in that case, the derivative with respect to y would be dx dy, kind of looking like the reciprocal of this, where y is in between c and d inclusive. So there are a lot of parallels here. In fact, really what you can do in that case, you can just switch x's and y's and you get the same formula used. Now here we have a kind of interesting type of problem where we are asked to find the length of this weird expression, y squared equals x cubed, from 1, 1 to 4, 8. Now, generally this is a little more than something you'll see. It's not as straightforward as a problem you would see in this section, but it's good that we see something not as straightforward so we can see how we can handle this. Now, actually, if you were to graph this, just to kind of explain a little bit, so 1, 1 is obviously over here, and 4, 8, let's say, is way over here, let's say. And the curve actually looks something like this. So we can find the length of the curve using this formula. The only issue is that we have to kind of make our decision. Do we use y in terms of x or x in terms of y? And as it turns out, they're both going to be the same. Now, when you get y in terms of x, so if you square root both sides, you get plus or minus the square root of x to the third. Notice that's just the same as x cubed, well, I guess x to the 3/2 is what I meant to say. But now notice, since y is always positive here, it seems, and you can kind of, again, verify this by graphing, that no matter what you plug in for x, as long as x is going from 1 to 4, which is positive values, y squared will be positive as well. In fact, y squared is always positive. But y would have to be, actually I guess y could be negative in that case, which is a little up for debate, but since we're going from this point to this point, we're on this part of the curve, not the curve below. So if we were to graph this, it would actually be, they would have two pieces, one above the x-axis and one below the x-axis. Which may sound strange, but remember, when y is squared, you actually have a curve that is not a function, so it possibly fails, and this one does fail the vertical line test. But anyways, I kind of digress a bit. I'm just kind of trying to explain that we don't really need the plus or minus. It ends up being all positive anyways, because the points give us the idea that it's above the x-axis. So we actually can use this. Now, if we do use this, then we can use the top version of the lane. And in fact, I'll use dy dx because I don't have function notation. If you want to call this f of x, by all means, you can do that. And notice what we need here, of course, we need dy over dx. And that's just going to be 3/2 x to the 1/2. So when we square this, our lane formula becomes the integral from, so remember, our integral limits are x values, and our x values here are between 1 and 4 for x, of the square root of 1 plus our derivative squared. Now the really good news is when you square this, the 1/2 power goes away. So this actually ends up being the integral from 1 to 4 of the square root of 1 plus 3 over 2 squared is 9 over 4. X to the 1/2 squared is just x. And this is a super simple integral to do. This is just a simple u sub problem because notice we have an inside of a radical. So in fact, look, if we let u equal 1 plus 9 over 4x, then that means du will be 9 over 4 dx. So that actually implies that 4 over 9 du can replace dx in our integral. So using this substitution, I hope we have enough space here, we now get the integral from, well, we'll have to change limits, which I'll do in a bit, of radical u du, but remember dx is replaced with 4/9 du, so let's pull out 4/9. And now let me try to change the limits here. When we plug in 1, our lower limit, we get 1 plus 9/4, which you write as a fraction is 4 over 4 plus 9 over 4, which is 13/4. So we have kind of crazy fractions going on, but that's okay. And if you plug in the top limit 4, this is actually a lot nicer because notice 9/4 times 4 is just 9 because the 4's cancel, and the 1 plus 9 of course is 10. So now what we need to do is differentiate, find the antiderivative of this. If we treat this as u to the 1/2, we can apply the power rule for antiderivatives. So that's going to be u to the 3/2 times the reciprocal of 3/2, which is 2/3, times that 4 over 9 still. Evaluate between 13 over 4 and 10. So really we end up getting, if you multiply this out, you get 8 over 27. Kind of border this off a bit. So we get 8 over 27 times 10 to the 3/2 minus 13 over 4 to the 3/2. Which I kind of want to, part of me wants to simplify this a little bit because it can be simplified actually quite a bit. And in fact, I'm going to erase and then I'll simplify just to show you. Alright, so I've erased the formulas here. I've left all the work though. So now I've rewritten our answer we left off on top here. And now let's see if we can simplify it. And the first thing I'm going to do is clean up this fraction part. So 8 over 27 is still on the outside, but now we have 10 to the 3/2 minus 13 to the 3/2 over 4 to the 3/2. Now 4 to the 3/2 cleans up really nicely. Notice since this is the same as 4 to the 1/2 to the 3rd, and 1/2 power means square root, this is just radical 4 to the 3rd, which is actually 2 to the 3rd, which is 8. Which is really nice because if you have 8 in the denominator, that means when you distribute the 8 in the numerator, it cancels out for the second term. Not for the first one, but for the second one it does. So I'm going to show that here. So I guess I'll just erase this part real quick. This is just to show that the bottom for the second term becomes 8. So now distributing that 8, we got 1 over 27 now. 8 times 10 to the 3/2 minus again, this was over 8, so you can think of this as just being 8. So when you distribute the 8 part only, you get an 8 for the first term, but a cancellation for the second one. And that's kind of it. That's really all I want to say, honestly. Something you can do is you can actually rewrite the 3/2 power as that number times the radical of that number. Because notice this is, just to show with 10 as an example, again, this is 10 to the 1/2 to the third, like we saw previously with 4. So it's radical 10 to the third, which is radical 10 times radical 10 times radical 10. But notice 2 of them just become 10. So altogether this is equal to 10 radical 10. And 10 radical 10 times 8 is of course 80 radical 10. And this one similarly, with very similar logic, is 13 radical 13. And that's all multiplied by 1 over 27. And that's where I want to leave off for this length problem. Now, I made a decision. I wrote y in terms of x. If you want to write x in terms of y and use the other formula I showed you, you can do that. We'll do some examples later on in this video that will actually use that formula. But now let's look at something a little more complicated though before we get there. All right, so for this example, we want to find the length of the curve y equals this expression in terms of x, where x is between 1 and 2. So the setup is fairly straightforward. Remember that the length, again, is just the integral between our restriction values, so those are our limits, 1 to 2, of the square root of 1 plus something squared, where that something is the derivative of our function. So notice if we write these two as powers, this is really 1/3 x cubed plus 1/4 x to the negative 1. So when you take the derivative of each of these, here the 3's cancel, so you just get x squared. Here, you end up with actually negative 1/4 x to the negative 2. So I wonder if we should leave it like, I'm actually going to leave it like that. So I'm going to leave it as x squared minus 1/4 x to the negative 2. You could write it as 1 over 4 x squared, where the x squared is in the denominator with 4, but I'm going to leave it like this, and you'll kind of see why shortly. So now the next thing I want to do is I want to expand this square out and see if we can kind of recognize a few things that, to be quite honest, are pretty standard types of situations that can possibly happen with these problems. In other words, you'll see something like this happen again, chances are, for an arc length type problem. This is kind of a standard thing you'll see happen. Doesn't mean it happens all the time, but you're bound to see it. So if we expand this out, notice we'll get the first one squared, which is x to the 4th, 2 times their product. This part is important. When you multiply these together, notice the x squared and x to the negative 2 cancel, so you end up getting negative 1/4 as the product. But then 2 times that for the middle term is 2 times 1/4, which is 1/2. It's a negative 1/2, of course. And then plus the second one squared. Well, when you square 1/4, you get 1/16. And when you square x to the negative 2, you get x to the negative 4. All right. So what is so special about this? Well, let's kind of recall that this part here happens from scoring this difference. Okay? Just keep that in mind. In fact, let me write that because that's a pretty important fact over here. So x squared minus 1/4 x to the negative 2 squared is equal to x to the 4th minus 1/2 plus 1 over 16 x to the negative 4. And you'll see in a second why this is an important fact and why it's good to write it down. The negative 4 barely made it on the screen, but that's x to the negative 4 as our last term. So now, getting rid of this emphasis, notice these two terms combined. 1 minus 1/2 is, of course, 1/2. But in reality, what happens is that in the radical, we end up getting x to the 4th plus 1/2 as our middle term now. Let's treat it like the middle term. Plus 1 over 16 x to the negative 4. Now, what is so magical about this, I think, is that really this is something we kind of already saw, only with a plus instead of a minus. So remember that for a binomial squared, if you have a minus b squared, the middle term is negative, but if you have a plus b squared, it's the same expansion, only the middle term is positive. So let me just write, if there was a plus here, then the middle term would be plus, and knowing that will actually help us recognize that this really factors as that being squared. So let me just write over here, this is the same as the integral from 1 to 2 of the square root of x squared plus 1/4 x to the negative 2, quantity squared, and again that's a plus in the middle, all under the radical, and then dx. And again, what's really great about this is that it cancels the radical. Notice, the square cancels the radical now. Otherwise, we may have needed to try a weird substitution, which you can try to do, but I'm going to tell you right now, it's not going to be pretty. This is really the best and possibly only way of doing this. Another alternative way of doing this, if this is too hard to recognize for you, is to actually not write them with negative powers and combine everything in one common denominator. The recognition's a little easier, but that's a lot more work for what it is. I think this is the better way of explaining and doing these problems as well. So now we finally have integral 1 to 2, no radical anymore, x squared plus 1 over 4, x to the negative 2 dx. This part is super simple because we can just find the antiderivative of each of these terms by, that's a negative 2, by power rule. Antiderivative of x squared is 1/3 x cubed. Antiderivative of this is, well, let's see. It's going to be x to the negative 1 over negative 1 times this. Because you add 1 to the power divided by that power. So it's going to be minus 1/4 x to the negative 1. Awesome. So notice really it's just the same thing we started with, but with a sign change in the middle. And does that always happen? You can verify that on your own, but I have a strong suspicion that kind of always happens. Okay, but anyways, it's just best to go through the motions regardless. So now if we evaluate between our limits 1 and 2, we plug in 2, we get 2 to the 3rd over 3, which is just 8 over 3. So let me write 8 over 3. And then here, notice 2 to the negative 1 is 1/2. 1/2 times 1/4 is 1/8, so that's minus 1/8. That's our first evaluation. And then when you plug in 1, kind of think the x's go away because any power of 1 is just 1 itself. So really we just get 1/3 minus 1/4 for the second term. All right, cool. Now all we have to do is combine. Notice that if you actually distribute this negative here, it's kind of nice. You get 8/3 minus 1/3, which is 7/3. And then you get positive 1/4. But notice negative 1/8 plus 1/4. If you multiply top and bottom of 2 to 1/4, you get 2/8. 2/8 minus 1/8 is just 1/8. So this is plus 1/8. And if we want to combine them into one fraction, that's going to be 8 times 7, which is 56, plus 3 times 1, which is 59, all over 3 times 8, which is 24. So I'm going to leave my answer like this, and now we can move on to the next example. Right, so this one is definitely a challenge. Notice I don't have limits given to us, so we don't quite know the setup as far as limits go. So we'll have to follow our nose with that, but at least let's try to get the integrand down. So notice it's going to be 1 plus the derivative of this crazy expression. Now, of course, if we write this radical as a 1/2 power, in fact, I'll do that with both of them. This may give us a little bit of leverage, at least to find the derivative anyways. Derivative of this, so let's call that dy dx, I suppose. This is going to be 1/2 times the inside to the negative 1/2, and then by chain rule, take derivative of the inside, which is 1 minus 2x. Now, derivative of sine inverse, if you don't remember, is actually 1 over the square root of 1 minus the inside squared. So notice when you square x squared, you just get x. So that looks like that, which is nice. But then, of course, by chain rule, multiply by derivative of the inside. Derivative of x to the 1/2 is 1/2 x to the negative 1/2, which kind of screws things up a little bit, but to be quite honest, it's not too bad. Because look, if we rewrite this without any fraction powers, or negative fraction powers for that matter, we end up with 1 minus 2x on top, 2 on the bottom, and the square root of x minus x squared. Good. Plus, this is going to be 1 over 2 times the square root of 1 minus x times another radical x, because x to the negative 1/2 is x to the radical x on the bottom. But notice actually, if you combine these radicals like this, and then distribute that x in here, what do you get here? You get exactly x minus x squared. So that's kind of nice that we see that happening. So things are kind of coming together. And in fact, when you combine these, now the numerators combine, so the denominators are right away the same. And notice adding 1 to this really just makes this 1 plus 1, which is 2, so we can ignore the second term altogether. And then we can go a little further by factoring 2 out, much like that, and then canceling these 2's altogether. So that actually looks really, really nice. Okay. Now, can we go further? We kind of can. But remember, we want to square this. So before I go further and go maybe over our heads with some non-obvious cancellations, I'm going to square. So if we square dy dx, which is what we needed for the formula for length anyways, that's going to be 1 minus x squared over this radical squared is just x minus x squared. And notice if you factor x out again, this is just x times 1 minus x. So we actually get that one of these actually cancels with the denominator. So in reality, this is just 1 minus x all over x for the square part. That's really good because that means the length, as far as the integrand goes, is just the square root of 1 plus 1 minus x all over x. And if you combine these into one fraction, notice since 1 is x over x, like that, then combining the numerators end up canceling the x's, so we just get the integral, that's equal to the integral of the square root of 1 over x. Wow. Crazy simplification happening here. And in fact, for arc length problems, that's really what's going to happen. The really nice thing about these problems is that I don't give you an integral to begin with. You're given basically this crazy expression, sometimes crazy, sometimes simple looking. In fact, it could be, that's the beauty of it. It could be a simple looking expression, but then out comes this crazy integral. In this case, we have the opposite actually. We have a crazy looking expression, but out of the arc length formula, we get this kind of simple looking integral. And of course, we can write this as 1 over x to the 1/2, which is just x to the negative 1/2, and then we can find the antiderivative from there and be done with it. In fact, I want to go as far as I can. So by power rule, add 1 to the power, you get x to the 1/2. Divide by 1/2 is multiplying by 2. Then just evaluate between the limits, and now we get to the power where we were stuck from the beginning. We're not given limits, so what do we do? Well, one option is to graph. I kind of feel that's a cop-out. So instead of graphing, I'm going to look at the domain of this. Because remember, the limits are the values that our x values can actually be, which really are the endpoints of the domain in this case. Now, in most cases, the domain is something like infinitely long, but in this case, since we don't have limits, and we're assuming basically that this is a finite segment anyways. So we want to find the length of the whole curve, which is kind of nuts that we can do that. So let's see, how do we find the domain? Well, recall we have radicals going on. So the inside of this radical is x minus x squared. So we know that must be bigger than or equal to 0. Otherwise, you'll have a negative and that can't be inside the radical. Now, if you factor this, this is x times 1 minus x, bigger than or equal to 0. And if you want to solve this, there are a few ways of solving this. Basically, either they're both negative or they're both positive, or else if they're different signs, and then the resulting product will be negative. So if they're both positive, that means x is positive and 1 minus x is positive. But notice if you solve this, you just add x to the other side, you get 1 is less than x. So actually that means that x is in between 0 and 1, because it's bigger than 0 but less than 1. So in fact what we end up getting there is that 0 is less than or equal to x is less than or equal to 1. Okay, that's what we get from just the radical part. Or again, if they're both negative though, so that can slightly change things. What if they're both negative? So we're kind of on a side quest to find the limits. So this is one scenario. And again, there are other ways of solving this inequality that may be more intuitive, but I'm just doing it this way. But if they're both negative, then notice this is negative, but actually, that's actually bad right away. So, I mean, we could continue this path, but let me just say that this actually never happens. And the reason why this never happens is because if x is negative, then we'll have a negative inside the square root from the sine inverse part. So that would be okay as far as this guy goes, but then if you kind of consider what has to be the case here, then we're kind of screwed as far as that goes. So what I'm doing is I'm looking at these two separate pieces, seeing what x can be for one of them, and verifying that can be the case for the other one. So notice here, if they're both positive, x and x minus 1 are both positive, then we get x being in between x and 1. And I verified that without saying it, that actually satisfies this. You can plug any number between 0 and 1 inside of a radical, and the resulting values you'll get will actually be in between 0 and 1, and that's well in the domain of sine inverse. Domain of sine inverse, by the way, is in between negative pi over 2 and pi over 2, so that radical must be in between those values. But yeah, so this actually ends up being, I believe, the limits anyways. But again, after a little bit of exploring, you can get that, but that's just a domain question, really. Or, like I said, you can graph it, which is not cheating or anything. Like, you can totally graph this to verify what's going on and get an idea, but I feel I owe you a non-graphing explanation. So with that being said, this whole time here, I guess is when the limits first pop up, they're actually between 0 and 1. Notice plugging in 0, you get the square root of 0. Plugging in 1, you get 2 times the square root of 1, which is just 2. What an awesome problem. So now I want to show you at least one more, so let's take a look at that one right now. Right, so here I want to do 2 examples. Notice one has x in terms of y, the other one doesn't. But it's just kind of to show that even if x is in terms of y, you basically just do the same formula only with x's in terms of y's. In fact, if you swap x's and y's, you get something pretty similar to this. And in fact, there's something kind of funny we'll see happen, and I'll kind of explain once you get to the second one, but these are super similar as it turns out. So the first thing I want to do is I want to find the derivative of this function here. So notice that in Leibniz notation would be actually dx over dy. So let me just write here that first we want to find dx over dy. Now if you recall, derivative of ln of anything is the derivative of the inside over the original inside. So derivative of cosine is negative sine, notice, of y, over the original inside cosine of y, and this is just negative tangent of y. Now since we want 1 plus this thing squared, our integral, we know our limits, that's going to be the length by the way, so let's call this capital L, will be of the square root of 1 plus what? Of 1 plus this guy squared. So if you square negative tangent, that's just tangent anyways, because squaring a negative gives you the same thing as squaring a positive. Also, when you square a negative, the negative goes away. Probably the best way of thinking of that. And something really magical that happens here, well, maybe not super magical because possibly this is by design of the problem. 1 plus tangent squared requires a trig identity, a Pythagorean identity in particular, which is secant squared. Perfect. Limits stay the same, of course. We haven't really done anything crazy. And notice the square and square root cancel out. And this is just the integral of secant, which we have seen before, actually. This is a kind of known fact that either we recognize that it's a known fact or we're going to be stuck for a while doing it. I'm not going to show how it is what it is. I've shown that in the previous video using the U substitution. There's actually a really nice way of doing it using partial fraction decomposition, which I think is more intuitive of an explanation, but this comes way earlier than partial fractions is shown. So for that reason, that method's not shown very often. But if you want to look into it, I would suggest trying it on your own. It's kind of difficult to see, but it's, I think, more intuitive than the other substitution way. Anyways, I digress. So what is the integral of secant of y with respect to y? It's, of course, ln of absolute value of secant of y plus tangent of y. And that's it. Now we have to evaluate between our limits. So it's not too bad. It's just a known fact, and it's not very exciting because it's this thing that you kind of have to remember. Usually it hits people left field, but we've seen it a few times where hopefully we're a little more familiar with it than we would be otherwise. But when you plug in pi over 3, notice secant of pi over 3 is the reciprocal of cosine of pi over 3. Cosine of pi over 3 is 1/2. So this is actually going to be ln of absolute value of 2 plus, well, tangent of pi over 3 is radical 3. And then minus, when you plug in 0, let's see. Well, secant of 0 is the reciprocal of cosine of 0. Cosine of 0 is 1. So the reciprocal of 1 is just 1. Plus tangent of 0 is 0. So notice we end up getting here is really just ln of 2 plus radical 3. Notice we do not need the absolute values because 2 plus radical 3 is the sum of 2 positive numbers, which is positive, so the absolute value of the number is itself. And for this part here, This is just ln of 1, which is 0. Great. But now what about this? Well, it's actually the same thing. The only difference is the limits. And we'll actually run through the same argument. I think it's not too hard to see. But let's see. So here we're going to find the derivative dy dx. And it is derivative of the top over the regular denominator. And notice derivative of secant is secant times tangent. So secant of y times tangent of y, secant of y times tangent of y, good. Over the original of the denominator, which is secant of y. Notice the secant of y is cancelled, so we just get positive tangent of y opposed to negative tangent of y here. And there's another way of seeing that really nicely. Since secant is the reciprocal of cosine, we can write this as cosine to the negative 1, and there's a log property that we can pull the power negative 1 out as a multiplier, so we get negative ln of cosine. Since the derivative of ln of cosine is negative tangent, derivative of negative that would be positive tangent. So it's really nice we can do that. Also, here I'm realizing that this probably should be of x. I kind of wrote that incorrectly. So these are all x's. So my mistake there. I got kind of used to writing y's from the previous problem, but this one should be y in terms of x, not x in terms of y. My mistake. But anyways, now the setup is going to be exactly the same, because notice when we square this, well, we get tangent squared plus 1, tangent squared plus 1 is secant squared. The square root of secant squared is secant. So really what this gives is the arc length, well, the integral of secant, which is ln of secant of x plus tangent of x. Notice the x's in this case instead of y's, between the limits, which are 0 and pi over 4. So the real only difference here are the limits. The problem ended up actually having the same arc length, even though the derivatives are slightly different. That one's negative, this one's positive. But as it turns out, when you square them, well, you end up getting the same arc length. So that's a nice consequence if you think about it. If you have two functions whose derivatives squared are the same, so the derivatives may be different, they're possibly negatives of each other, but if the derivatives squared are the same, then they have the same arc length, given the same x restrictions. Anyways, notice when we plug in 0 here, we already verified that's just going to give us ln of 1, which is 0, so that's taken care of. And now pi over 4, well, we know it's going to be positive because secant of pi over 4 and tangent of pi over 4 are both positive, so we don't need absolute values now. Cosine of pi over 4 is radical 2 over 2, or the reciprocal of radical 2. So notice radical 2 over 2 is just the same as 1 over radical 2 is what I'm trying to say. So that means secant of pi over 4 is the reciprocal of radical 2, which is just radical 2 itself. And tangent of pi over 4 is just 1. And that's of course because tangent is sine over cosine, and sine and cosine are both radical 2 over 2 at pi over 4. So tangent of pi over 4 ends up being radical 2 over itself, and any number over itself is 1, so we get that. Nice. So I think this was a fine way to end 8.1. We didn't see too many exciting ideas, but we at least saw a formula for arc length that actually spits out an integral depending on what you want to find an arc length of. And this kind of sets the tone for essentially all of chapter 8. So in section 8.2, which we'll be seeing next, we'll actually be taking a look at surface area of revolution. So it's kind of like a volume of revolution, if you've seen that before. So basically you rotate a curve about the x or y axis, you get a solid, like a three-dimensional solid, and normally you'd find its volume from like chapter 6 is where you learn techniques of that. But here we're going to actually find the surface area, which is a nice application of integrals, and a lot of kind of pretty heavy chapter 7 techniques may possibly creep up there. In fact, some of them may possibly creep up here, even though we haven't used anything crazy here. This is from 7.2, and that's really the craziest we got. There are problems here that may require trig sub, which makes sense because notice we have radical of 1 plus something squared. So if you're taking a look at, let's say, y equals x, or I guess it would be y equals x squared, its derivative would be 2x, and then squaring that would be 4x squared, and 1 plus 4x squared inside a radical actually requires trig sub. So keep in mind chapter 7 techniques would be applicable in chapter 8 a lot. Anyways, I hope you enjoyed this video. I'll see you in the next video for 8.2, where we'll discuss all that fun stuff. And thanks for watching. See you then.